pressure of A is here, here, here. I don't know anything. All right, so let's just look at C by itself in a vacuum. Again, if I'm not at equilibrium, or now am I approaching equilibrium? Because this is going to 0. I think you guys are right, though. I think it's A and C is on the surface. I think that's the most consistent way of looking at all the data. And so what rate equation could I write down? So the rate of consumption of A, some rate constant, I don't know, times what should go in the numerator? And now you could put in, and we will, just because even though we might be measuring things away from equilibrium, it told us it's reversible, so let's include the reverse reaction. Let's assume it's elementary, and so you get what goes here? Do I need a rate constant here? Yeah. Because I have this factored out, I need the equilibrium constant for the reaction. And now what's on my surface? And how many sites does it need, presumably? Do I know anything about the number of sites? I think 2 is a good guess. You can theoretically tell by the way that that changes shape, but it's kind of hard to do that on, without using like math. So what do I have on the surface? Do I have any empty sites? Yeah, at least at this regime. And again, if I'm writing the rate equation for all regimes, then we want to include the empty site term. Do I need to include a term for A?
Yes.
So what does it look like? And then C? Same, right? But not B. I think that's about all it asks. The linearization of the data, you guys learned data linearization a long, long time ago, but you can do it. You would do it on this equation.
Just plot versus P squared.
How'd you get squared?
Yeah, something like that. You might do a log.
How'd you get squared from like denominator?
Oh, I'm guessing. It's a 2A to B plus C type of reaction. It's a guess. Technically, again, you can tell by the shape of this, but what you would do in reality is you would fit both, right? Just put down both rate equations in Excel. You would fit the parameters that you don't know and see which one matches the data better.
Does it not actually ask you to propose a mechanism and stuff? Does it justify?
I don't know what it says. Derive a rate law and suggest a rate limiting step. So if we, the rate limiting step 2A star to B star plus C star.
So if we set the homework just 2A star goes to B.
You're not going to lose points on a homework problem. If you did it, you're not going to lose points. And I guess another obvious hint that A and C are what's on the surface is that part E asks you to come up with the number of A and B and C on the surface and auspiciously leaves out B. All right. Let's do an example from an old exam. Fixing your homework? Juan's got no shame.
One, not for great, but you did it, you get it right.
Yes.
I just had a question about, you already believe the graph, but the second one asked about the reversibility of the equation of like.
How reversible things are?
Yeah. Is it because?
No, it's a good question. If the reaction were somewhat reversible at these conditions, then increasing the amount of B would decrease the rate. The rate would again trend towards a net rate of 0. But since it's flat, flat doesn't mean rate of 0, right? That would be if it was showing you the concentration. So the fact that the rate is non-zero and unaffected by the concentration of B does give you an idea that you're far from equilibrium, and therefore at these conditions you're rather irreversible. But I think when you're deriving a rate equation, it's better to be safe than sorry. Yes?
What would the graph look like if these were
desorption we're rate limiting? So I mean, again, the only thing you do for that, so let's just imagine it's A plus star goes to A star. A star reacts to form B star, and B star reacts to form B plus star. So if you're going to say this is rate determining step, that means that both of these steps are then what? Quasi-equilibrated. And then the rate of the reaction is equal to the rate of the rate determining step, which is equal to the rate of step 3. And we wrote that as irreversible. We'll write both of these as reversible and quasi-equilibrated. So what is the rate of step 3? K3, concentration of B star. And what is B star? Which type of K? Big K, it's quasi-equilibrated, 2 times A star. Now, is that correct as written? K2 is equal to B over A, so yeah. And now what is A star?
A1 A times star. A1 BA times star.
Any questions so far? This goes into this goes into this. And so you get R3 is equal to K3, big K2, big K1. And then instead of B star, what goes here?
PA star.
PA, and then star. And then what do I do with this? Side balance, just like every other one. In other words, a desorption limited reaction or an adsorption limited reaction, treat them no differently than you would a surface reaction limited reaction. Unless I was asking you about the details of this K, because K for adsorption are different from K for surface reactions or desorptions. But we're not going to talk about that. So again, just find your rate determining step, everything else quasi-equilibrated. Now if it's reversible, your rate determining step, then you have to make everything that follows it also quasi-equilibrated. Does that make sense? So if I have another step here, if this is not rate determining, but instead this is rate determining, this is still reversible and quasi-equilibrated. If this is irreversible, does this reaction matter? No, this reaction doesn't show up. So it doesn't matter if it's reversible, irreversible, quasi-equilibrated. It makes no difference. It literally never shows up in your rate equation. But if this reaction is reversible, then this one also, you're going to assume, is quasi-equilibrated. At least within the context of this course, you're always just going to assume that a single step is rate determining. Now, does that have to be true in reality? No. Most of the time, it actually is true. All right, the example that we're going to do where's the problem start? Is going to deal with the dehydrogenation of ethane. So the reaction, the way that it's written is this is ethane. And it's reacting with two sites to form RS plus HS. So what is RS chemically? C2H5 star, right? We've lost an H. So from RH to this H. So R here is obviously just representing an alkyl fragment if you think about chemistry. And then the next step, and you're given the at least what to use as both the equilibrium and rate constants for all these reactions. The next step, RS plus S ES, I'll define E in a second. This is big KR, little kr, and E is ethylene. So he puts negative E there to indicate a desorption. I don't know what C is supposed to indicate. Caffeine?
Would two HS's come together to form?
Yeah, we're not done yet. I just wanted to explain what this meant. But yeah, you already know what's going to happen. Again, he puts negative H there since it's a desorption instead of an adsorption. Like, a lot of times within literature, what you're actually going to see is that people will write these, even though they know that things have to desorb, they'll still write them in the direction of adsorption and just use standard adsorption. And we did that in the last example, right? When we did it for C, we didn't put Kc with desorption, we put Kc for adsorption. That's normally what people do. I don't know what I'll do on the exam or anything, but just don't be flummoxed by either one. Okay, it says derive rate equation for the rate of ethylene production, assuming that ethane chemisorption is rate limiting step. And it says write the equation in terms of